about event orchestration with MassTransit state machines.
Thank you very much. My first mistake was not including a About Me slide. So my name is Brendan. I work at Mantel Group. I'm a lead software engineer, mostly in the .NET space, but I like getting my hands dirty in whatever code I can. Even JavaScript. I'll even do some JavaScript and like it sometimes. Testing in JavaScript is fun. When you have to mock things, it doesn't care, and you can just put whatever you like, anywhere you like. So I'm going to talk about event-driven architectures and using MassTransit. So I'm going to start just by running through some basic event-driven concepts, just to kind of introduce some of the themes we're going to be using. And then I'm going to introduce a use case. So I'm going to actually build the back-end part of an application. I never had enough time to build the complete application and give us all a nice game to play, but the use case stands as a way of introducing how to implement these things. Then I'm going to introduce the MassTransit library and talk about sagas and state machines. I'm then going to cover how to test MassTransit with unit tests. I'm going to expand that to adding some persistence to MassTransit and do some integration testing. And finally, at the end, I'm going to look at deploying to AWS with CDK. AWS isn't my kind of go-to thing, but I had an AWS project last year, so I'm like, well, I'm going to write some test code then. And so for this project, I decided to use AWS just to get my head around CDK, which I quite like. For many, many years, web servers have looked like this, not all the time, but most of the time. You've got a client, and the client sends a request to a server. And while that request is happening, the server is doing its work, the client's sitting there waiting for a response. If the server takes too long, it's going to time out and you won't get anything and you have to retry it. Now the client can be smart and can retry. But in that one transaction or that one instance of a request, you send the request in, the server receives the request, it builds the response, sends the response back, and that's a unit of operation. That's a HTTP post, it's a GET, and that's how a lot of applications work. When we started moving to service-oriented architectures, we started to see this more and more, where we're starting to push out our functionality to a bunch of different servers, maybe around bounded contexts. But if it's all built on top of HTTP, what's happening is, while that first request is coming in, it's now waiting for a whole new request response cycle on those downstream dependencies. So your fragility is going up every single time. And obviously, you can make each of these clients smart, put poly in there, get them to retry. But the fragility of the application grows as you add more and more complexity to this system. So let's introduce the concept of a queue. A queue, instead of everything being request response, I'm going to send a request, I'm going to get a response back in that one operation. If you introduce a queue, your messaging becomes asynchronous. I'm going to drop a message into a queue, and I'm not going to sit around waiting for it. Something else will later come along and pick up that message from a queue. If you absolutely have to have a request response pattern, sometimes you do, you can still do request response through a queue, but now you've got two queues. So your request goes into one queue, gets picked up by the consumer later, the response goes into the second queue, and eventually comes back to the producer. Now, this is all achievable, but it's much better if you can design your system to not require request response, to not have some user waiting for those two queue operations to happen. One of my favorite things with queues is they add resilience. If you put a message in a queue and the receiver tries to pick up that message and for some reason it fails, especially if it's a transient error, like I couldn't connect to my database, there's some downstream thing that's no longer available to me, it'll drop that message back into the queue. Later on, it can retry that same message, and maybe this time it works, especially if it's a transient message, transient failure. So what these queues can give you is what's called at least once guaranteed delivery. What happens is when you, in fact, I'll go to the next one for this one. So a factor that kind of comes in with that guaranteed once delivery is a pattern called the competing consumer pattern. I can drop a message into a queue and I don't need to care about how many independent consumers are sitting there waiting to process messages from the queue. So no longer am I saying I'm one client talking to one server. I can put it in the queue, I'm decoupled, and then those consumers can compete over who gets to pick up the next message. If one consumer is too busy, the next one will pick it up. And the producers need to know which one it did. Now, for this to work with guaranteed at least once, it's best if the consumer, when it tries to first process the message, it places a lock on the message, and different queue systems have different ways of doing this, but if it places a lock on the message while it's queuing it, while it's processing it, that lock will have a timeout. If the consumer fails to deal with that message within the timeout, it'll then go back onto the queue. But if the consumer comes back to the queue provider and says, yep, I've processed that message, it's received, you can take it off, it'll then take it off the queue and the other consumer will no longer see it. So you place a lock, work on the message. If that times out, it will go back on the queue, or if you say it failed, it'll go back on the queue. But if you have finished it, you'll receive it, it's now gone, the other consumer doesn't see it. One more design pattern you can get with messaging is topics or pub sub. So with this pattern, we've got one message coming in and one consumer coming out. But if you want to do a one-to-many pattern, that's where a topic or a pub sub pattern comes in. So I'll drop a message into a topic that might get pushed out to two queues. And this structure is how both Azure Service Bus and Amazon SQS does this kind of thing. I'm not sure what's going on inside of RabbitMQ. I also know that Kafka, which is another queuing system, does things slightly differently. Kafka keeps all messages, but keeps track of which consumers it's seen and which consumers have received which message. So Kafka will keep everything in the central queue, but as a consumer, you say, I'm consumer one, give me my next message. It will keep track of which message you've seen. But it gives, at the end of it, the same type of thing where you can publish one producer out to multiple consumers. And again, what you're introducing here is decoupling. Your producer needs to know less and less about what the consumer is doing, apart from the fact that a message has gone out and someone's going to deal with it. So this computing consumer pattern scales exceedingly well to serverless. Because what you can do with serverless is if you place your message into one of the core queues provided by that service provider, say for example in Azure, you've got Azure Service Bus, you've got triggers in Azure for function apps that will then wake up function apps and run function apps to deal with that queues and spool up load and deploy more function apps in order to deal with that queue. So the competing consumer patterns there, along with automatic scaling up and scaling down to handle your queue. And then Amazon, the same thing would be SQS. So you drop a queue in SQS, you start up Lambdas, and so again, you've got that completely scalable compute to deal with your message queue and message throughput. The next topic I want to introduce is the concept of choreography versus orchestration. So we've looked at sending one message through or sending a message to a topic and message going to multiple places. But there are two fundamental kind of ways of organizing your architecture around those messages. Choreography is kind of like people in a dance. Everyone's dancing around, they're passing things to each other, they're meeting up, they're splitting apart, but no one person is in control. So choreography is quite easy to set up because you just write the code for what that thing does, but then the bigger picture is harder to keep track of because individual systems are passing messages where they need to go, but the big picture isn't that easy to keep track of. Orchestration is more like an orchestra where there's a single conductor keeping track of everything that's going on. So with orchestration, it's very easy to find out what's the current state of things. So just ask the thing in the middle. But the downside of that is it's more tightly coupled in general. Obviously, it's possible to make tightly coupled systems with choreography. It's possible to make fairly loose systems with orchestration. In general trends, choreography is less coupled than orchestration. And that just sort of says what I've just said. So today's talk is really going to be focused on orchestration because typically when given a problem, my go-to is choreography. I like decoupling things as much as possible, even if it makes kind of overall tracking of things harder. But today, the point of this talk was for me to learn a bit more about orchestration and techniques in order to make orchestration work. So with orchestration, you've got this orchestrator. Another word for an orchestrator is a saga. Now, the whole point of a saga is it has state. A message comes into the top and initiates that saga, and that saga has some data in it, probably received from the messages, maybe some data it's created. And then that saga can then contact a dependency. Now it can do a direct HTTP request. It could be async request and async response. The key thing with handling that async response is a saga wakes up, loads its previous state, and then process that response. So it knows, I've already had this thing come in, I've already asked that thing down there to get something for me, I now know what to do, I've got the response to process, and goes forward. Now it is possible to implement workflows without a stateful saga, but in that kind of pattern, you put your state inside the messages. So here's a pattern that I've sometimes heard called, or I've definitely called it the enrichment pattern. I've got an order received message coming in. And when that message coming in, it's details of the order, but that message doesn't contain the payment details because we haven't done the payment yet. But if I send that next request off, including enough state, to a payment service, then when that payment service completes its thing, it sends back the same message type, order received. But this time the order received has extra state in it, has the payment details as well. So this event handler now, all it has to do is look at the message that came in, said, do I have payment details yet? No, I'm going to call the payment service. I've got payment details, now I can forward the fulfillment service. So I've got state, but there's no external state in that handler. The state is baked into the messages themselves. The final topic I want to introduce as a concept before we start building applications is the concept of a state machine. So a state machine is a way of modeling a problem where you've got two key components of it. One is the state itself. So here's a state machine diagram for a button. The button can be on or off. In this case, there's one thing you can do to that button, you can press it. So if you raise the button pressed event on an off button, it becomes on. You raise the button pressed event on an on button, it comes off. Let's take a look at a more complex example. Here's a slightly more expensive light where it's got 3 light levels. It can be dim, medium, or bright. And every time you press on, it cycles through those 3 states. Every time you press off, it turns it off. So the whole point of state machines is you can definitely keep track of these 1, 2, 3, 4 values. Maybe that's an enum with off, dimmed, medium, or bright. But the point of a state machine is don't let you just write to that piece of state anywhere. The only way to change that state is to fire one of the specific events. And in this sample you can see there's no way to go straight from bright to medium. You can't just go to a bright light and change its state and say you're now a medium light. You have to press on twice to cycle through. Okay, so we've introduced a few core concepts on kind of architecture and state machines. So let's look at a use case. I wanted a non-trivial use case of something that's kind of fun to build that obviously would be great if I had a fully working game where you can all get our phones out and play. I didn't have time to do that, but I built the back end for it. So my non-trivial use case is obviously an online trivia game. So we need to support multiple users. There's going to be multiple choice trivia questions that we play together in a game. We're going to use the Trivia API, which is a free online resource that will give us questions. We want it to make it a little bit fun and interactive, so let's assign points to people based on how quickly they answer. That gives us a bit of logic to work on. So it's also an example of a problem that's stateful. We go through a bunch of states as we work through the game. It's got a workflow, and events are coming in from multiple sources. There's timed events, and there's users pressing buttons to cause events. So what we're going to do now is walk through the events and the states we're going to model in order to create our game. So we start off, and everything starts with an event called create game. We're going to create a brand new game. And into our state, we're going to put a correlation ID. So that's the key ID that identifies our game throughout all the messaging we do. We're going to give it a name. Now, at the end of the create game event, we're in a state called lobby open. While lobby is open, we can accept new participants to join our game. So during this phase, we'll accept the add participant event, and it will add more participants into our state. Calling add participant at any other point in our game is meaningless, and it won't let us do it. So the whole point of the state machine is to constrain what events we can do at any one time. Some point we've had the lobby open for a while, and people have joined the game. So we go, all right, let's start the game. As soon as we hit start game, we're going to trigger another asynchronous event to go and fetch some questions for us to play. We're going to save those questions. We're going to increment the current question number to question 1. And our state at the end of this action is question open. The next thing we're also going to do is we're going to fire a scheduled event. So one thing you can do with messages is put a message into a queue, but say, don't deliver this message for X amount of time. So our question is going to be open for 10 seconds for people to put their answers in. So we're going to schedule an event in 10 seconds time to close our question. So we're now in the question open, and now we can accept answer question events. Now the answer question event isn't going to change the top level state of our application, but every time our answer question event comes in, it's going to append extra answers into our state. Then after a certain amount of time, our scheduled close question event comes in. It's going to push us into the question result stage. So the question result stage is, okay, that came through. It will tell people if they were right or wrong. But it will also run a process to calculate our scores. Because remember, every time we received an answer, we can tell whether it was right or wrong. And based on the timestamp that we received that answer, that's when we can give them a score based on that. And because we're using async messaging, we should be confident on the time, because the time is when it hit our queues, not when we got around to processing it. So it's time critical without us having to write extremely reactive time critical code. The only reactive time critical code is getting the message into the queue. We can calculate scores. We can take as long as we like, because that's not time critical, it's happening after. So then we'll go through, after we've been on the answer, we'll schedule the next question, we go to the next question, schedule code question, and basically we'll walk through this process until we get to the end, and we end up with our final state where we know everyone's questions and answers, and we've got final scores to display. So that's our use case. We're going to build a game. We've seen all the different states we can build. We've seen all the different events. We're going to fire out our use case. So the next topic, we're going to look at the MassTransit library and show how we can use this library to build this application we've just spec'd up. First of all, MassTransit is an open source .NET library. The core thing of MassTransit is it's kind of a wrapper around multiple message libraries. And in fact, it supports all of these backends to support your messaging. So you can use Amazon SQS, RabbitMQ is really popular MassTransit if you want to do it all on your own machine. That's a good answer. Service Bus, Event Hub, and even Kafka. So let's start by configuring, and as you can see, the core items, your consumers, your producers of MassTransit, are the same regardless of what transporting framework you use. You select the transport framework by just picking up. So I'm using Amazon SQS, so there's a big chunk of code inside your MassTransit configuration that says use Amazon SQS. So at the start, you've got builder.services to add MassTransit. That's wiring MassTransit itself into your dependency injection container. You've got kebab case endpoint name formatter. That just really sets up how MassTransit names the various endpoints it's going to send your messaging through. And finally, we've got use Amazon SQS, which is where we send the configuration of how we talk to our Amazon messaging service. So let's take a look at how we can then send messages using the MassTransit library. Now to send a message, sending is like, I know where it wants to go, so I'm going to give the name of the endpoint. I'm going to say I'm sending a message to that point over there. So when you send, you inject an iSend endpoint provider. You give it the name of the endpoint you're talking to, and then you can just send your object. Producers are a little bit more interesting, and I use producers pretty much exclusively because of that decoupling aspect. Producers are, I'm going to publish this message. I don't really know who's going to pick it up, but MassTransit will work it out for me. So whatever systems I've got that are set to receive that message will pick that message up. And so all I've got to do is get myself a publish endpoint, publish that message. And in this case, I've got my create game, this previous one. Anytime you see kind of generic code, it's because I didn't actually use that particular pattern in my application. So that's sending an order. Here's one, but I'm actually doing a create game message through. So we can send a message. We can also schedule a message. We can do a scheduled send or a scheduled publish. When we do a scheduled message, we just send it, and then we give it a date stamp, time span from when we want to send it. Actually, it's now plus time span, so it's date stamp. What we can also do with MassTransit, and this is very cool, is the asynchronous request response. So once again, this isn't the same as your HTTP request response. With MassTransit, what we're doing here is we're putting an asynchronous message into a queue. We're going to await from the client side and wait for an asynchronous message to come back from the server or from whatever service picks up a message on another queue, and we're going to then accept it. So this is a client that's going to wait. It's asynchronous message going on behind the scenes, and there's quite a lot of smarts behind this, because when the message goes out, it's also got address details in its envelope telling it which service to route back to. So if I've got a pool of clients and a pool of servers, it will actually identify which server to come back to. So quite a lot going on behind the scenes to allow that to work in really quite simple code that looks like a HTTP request. So we've looked at sending messages. Now I'm going to introduce the various objects you can use to consume a message. And the most simple of those is a consumer. So if you create a class and implement the iConsumer of type your message type, you can then create a task. iConsumer defines the consume method. You implement the consume method, it comes in with the consumer context, and you can then handle that message. You can also use the context to actually fire more messages. So we've got a submit order message coming in. We're going to do some work in here, but when we're finished, we're going to raise an event saying order submitted. So we're using a consumer in our application to handle the fetch questions system. So what we've got is we're receiving a fetch questions message. We're going to inject the HTTP client. We're going to use the HTTP client to go and fetch some data. And then when we're done, we're going to send another async response back. So that's a consumer. It's a class that can process one message. The next thing we're looking at is a saga. So to make a saga, you implement or you extend iSaga, and you put the initiated by at the top there, says this is the message type that starts off this saga. Then you put some state. So any properties you define in that saga, depending on how you've configured your state for the saga, and we'll get to that later, that's the stuff that will get saved. So MassTransit will save that stuff for you as per whatever persistence you've configured. And then you can have multiple messages inside the saga. So there's two key things about the saga. It's stateful, it will keep that state, and it can have multiple messages targeting it. So you can have it send something out, receive something back later, keep waking up and shutting down again. So the final thing I'm going to show you is we've seen consumers, we've seen sagas. The final one is a state machine saga. So a state machine saga builds on top of a saga that has state to also make that state also implement a state machine. So the first thing I'm showing you here is a game state object. We've now turned our game, we've got the actual state we're going to store about our application. We've got the correlation ID, which is the magic key that ties everything together. We've got this thing called current state, which is the state of our application. That'll be whether we're in lobby open, whether we're in a question. We're keeping track of which question we're currently on. And then we've got a list of participants, questions, and so on, question answers, scores, all the information we need about our game. So then once we've defined the state for our state machine saga, we can start implementing our code. So what this piece of code here says, that initially, when the create game record create game event, is raised, we'll transition to the lobby open state. So what we've got here is almost a domain-specific language inside there for defining our state machine through this declarative language. So let's take a look at that a little bit more. During lobby open, when the add participant event comes in, then we'll use our context to grab participants from our saga and we'll add that extra message, that extra participant, into the state for our saga. And for the add participant, we're not going to change the state of our application. So we're going to repeat this operation as participants join in while the lobby is open, and we'll keep adding to our list of participants. Later on, when we call start game, we're going to fire a request. We're going to fire a request to fetch questions. And then when that's done, we're going to transition to the fetch questions and request pending state. So now we're in a sort of sub-state of we're waiting for those questions to come back. So once again, we've declared the state there, lobby open. We've got an event that we raise that may transform our state or may have something else happen. It may transform our top level state of what state are we in, or add to other internal state, like in this case, the list of participants. We can also raise more asynchronous request responses during the processing of a particular event coming through. So what we get with MassTransit is this really nice, really concise way of defining all the steps we've just explored, all the different events and the state changes we need to make in order to build our game. We can also call the scheduler to schedule the future events, all those timing things like the questions open for 10 seconds. Once the question's closed, we'll display the results for 5 seconds and then go to the next question. All that stuff is handled through raising timed events at specific times in our flow. Okay, so that whole workflow you saw looks really nice. It's really easy to read and follow. But in order to do that, you do have to declare a few things in your class. So the actual state machine class is quite big. We've got to individually declare all the states we want to use in that flow. We've got to individually declare all the events we're planning to use in that flow. We've got to individually declare also things like the requests we're going to fire and the schedules we're going to call. So for stuff to slot into that really nice flow, we do have to elsewhere in the class just declare them all. And it's a big just chunk of declarations. So next thing I'm going to go into, okay, we've got these things called sagas, we've got these things called consumers. How do we wire them up? Well, we just wire them up inside our dependency injection container. There's a few ways of doing this. If you want to configure it manually, you can just say, okay, add a consumer, add a saga. But I quite like kind of convention over configuration. So this code you're seeing here is just introducing assembly scans. So scan this assembly, pick up all the consumers you find and wire them up. Pick up all the state machines you find and wire that up. So that's an introduction to MassTransit, and we've shown how we can build our application in this really nice kind of event-driven and this event has this consequence way. How are we going to test this? And this is one of my favorite things, because we can now test this stuff on my machine without having to actually put it into a messaging provider yet, or deploy it to the cloud or anything. So the first thing we can use when testing, one of the providers you've got for messaging is just in memory. So if you want to just try something out, using memory providers, you'll see messages flying around, you can confirm it works. And that's pretty useful, but not quite as useful as the second option, which is the MassTransit test harness. So the MassTransit test harness, like a lot of test harnesses you're seeing these days, it's kind of like very similar to how you'd configure MassTransit in the first place, but it's now in a test context. You're kind of configuring the same configuration in this test harness, and then you can start that harness and start running things through the MassTransit engine without spooling it up for real. So the advantage of the test harness over just using in memory is you can actually query things in the test harness. So you can, not only do you have messages going in and messages going out, you can query the test harness and say, oh, what happened there? What state did we end up at? So in this case, we can start up our test harness, we'll publish the create game, and we can confirm that once we've finished, the current state is lobby open, and turn that all into asserts. So we're writing asserts around all those logic, all those rules we've made. We can also use our test harness to make sagas. We can set up our sagas in custom initial states. So I don't care what happened 5 minutes ago. If I have a saga that starts off in the question open statement, and then I do something, what's going to happen next? So what this means is I can test that whole game engine there in memory with unit tests very fast and confirm that all these different events and triggers are set up the way I want them. Once I've done that, I can move on to persistence and integration testing. So MassTransit supports a lot of different engines for the event provider, the messaging provider. It also supports lots of different engines for the database, from Entity Framework and Azure Cosmos DB. You can use Redis caches. The one I wanted to try though, because I'm a massive fan of Postgres, is this one, Martin, .NET Transactional Document DB and Event Store on Postgres. We're not going to use the Event Store today. That's something I want to play with soon. But we are going to use the Document DB aspect of Martin. So how do we configure Martin? Pretty simple, just like any other thing you configure these days. You have an add myself name for the service collection. So you say add Martin, and you just pass it the Postgres settings. Then when you want to then use Martin with your Saga, that bottom line, add Saga repository for game state, is I'm saying I want to store my game state in this Martin repository. So that's how to configure it, but how am I going to test it? How am I going to test it with a real database? Well, that's where test containers come in, because I want a temporary instance of Postgres that I can actually make sure Postgres is going to save my state and then throw it away. So containers are great for temporary pieces of infrastructure, but what test containers does is it basically takes the ability to create Docker containers and binds it in a way that it's easy to call from inside your tests. So inside your actual unit test code in C#, you can say, give me a container, feed in these settings, start it. Now, I've said before I love Postgres, but a lot of that love came through almost Stockholm syndrome, because when I first started to use Postgres, it was pretty hard to get running. I was on a Linux machine, I had to install from the package manager, and when you install Postgres from a package manager, it comes in with pretty much everything turned off. So you've got to dig into the config file and learn how to set up TCP/IP. TCP/IP is turned off by default when you install Postgres. But when you're talking test containers, I found it a completely different story, because when you go to testcontainers.net, not only is it the library to have that bindings between your tests and the containers, there's also a bunch of pre-configured containers that are set up ready for use in testing. So these are containers that are there for testing, and so have things turned on and will work first time. So in order to use a Postgres instance in my tests, this is pretty much the only code I had to make. I had to pull in testcontainers.postgres. I go PostgreSQL builder.build. I start it at the start of my test, and I dispose it at the end of my test using the async lifetime interface for XUnit. Then inside my test, that same Postgres container has a connection string, so I can now start spooling up my MassTransit instance inside my test, feed it the connection string, and bang, it works. So here's the arrange of my test where I'm setting up the services. In my act, I am taking my test instance of MassTransit. I'm manually kicking off the bus, which is the system that routes messages, and then running the publish. And then for the assert, I'm connecting to that database itself and actually finding that, that record that was created. How did I dig into the Postgres itself? Well, what I did is I breakpointed my test and jumped into take a look at my containers. This is the list of containers you've got while your test is breakpointed. Postgres is the container I asked for. And this second one, test containers /ryuk, is a container that test containers puts in place to make sure that all the other containers get killed when your test is over. So even if you do something wrong with your test, you're guaranteed to clean up after itself. So it's part of the test containers framework. But with my test breakpoint, I can then go and log in to Azure Data Studio, take a look. I asked for something called GameState, so Martin created something called mt.GameState. If I look in there, you can't see very clearly, but there's a big chunk of JSON in there somewhere. So it's just a single record. All my data is in a big chunk of JSON, and if I expand that JSON, it looks like that. So that's my state in JSON. So we've looked a bit at MassTransit now. It's a library for working with async messaging. It allows you to use things like consumers. You can send, publish, schedule, and request. You've got sagas, which are stateful. And they can orchestrate model consumers and model message handlers into a single thing, and all will work together on that state. You've also got state machine sagas that builds on the state to add a state machine framework, which means you can work on your application with that fancy state machine workflow syntax. A few caveats about this design. This is definitely a test design. One thing I've got right now with how this is working is I'm loading and saving the full state from that one record every single time there's a message handled. That works fine for a game with maybe 10 to 20 people. But if you get 1,000 people playing the same game, suddenly you might get some contention on that one state. So what I would do to make this more scalable is, well, some of those events that are being handled are writing to the core game state, and they need to kind of, they happen quite infrequently. But those high frequency ones where users are doing something like adding to the list of participants and sending in a response, I'd peel that off into a separate piece of state, so there's no contention. So every time there's one participant answer coming in, there's one record going into a database, something like that. So we've looked at persistence and integration testing. The only thing that remains is for us to deploy this somewhere and actually get a working application. So expanding on this a little bit, I'm actually breaking this out into slightly bigger architecture. I don't have this complete to the point where we can play the game together, but this is the architecture you'd run the whole thing on top of. Most of the things we've looked at would sit in that back end, that MassTransit saga. Then in front of that, an API is basically a straightforward back end for front end that's going to just give us endpoints that our client side will talk to. And maybe I'll replace that with Signal and even make it more eventful or some alternative. API gateway sits in front. The API gateway sits in front on all Amazons. Unlike Azure, where the kind of API gateway type thing is quite expensive and it's an option extra, you just get API gateway with Lambdas. They have some other products that do a bit more, but in order to even route any traffic to Lambda, then the API gateway is involved. So here's a really early version where I've only created one endpoint to kick off the crate game, but that's what's going to build up the actual application. But that Lambda, that API Lambda, is an ASP.NET Core web application. So one cool thing that Lambda has that functions don't is when you write functions code for Azure Functions, your code has to be written for functions. With a Lambda, you can take an ASP.NET Core web application and turn it into a Lambda. Now, it's not going to be that good if your particular application is stateful, because the Lambda doesn't live very long. But for the purposes of just handling a few requests now and then and shutting down, then what you do is you just pull in to your .NET application, build it at services, add AWS Lambda hosting, and that will allow your application to run as a Lambda, even though it's a full ASP.NET Web API. Again, you configure your services. Here's where I've configured using SQS to send the messages through. HTTP pipeline for that is pretty standard. And then, I've got a HTTP controller class, MVC controller class inside my Lambda API. So the code you're writing here now is the same as a .NET. It's not special because it's being run from a Lambda. So I inject my publish endpoint, and when the create game comes in, I just publish that endpoint, and that gets sent off to the messaging gets sent off to Amazon SQS, and then gets picked up by my backend Lambda and kicks off my state machine engine. So I've looked at a few infra as code options. So CloudFormation is kind of AWS's version of ARM templates. Lots of markup, really not that friendly. Terraform's the kind of bigger and more popular one. That helps you a bit, but it's still markup code, it's not real code. CDK, or the Cloud Development Kit, is my favorite thing for deploying to AWS, because what you use in CDK is when you're building up the structure that you want to deploy to the cloud, you actually write code to do that. So that, say, it's a bit like Pulumi. Pulumi is very similar to this. But you write code in your favorite programming language, build up the structures, and that compiles to a CloudFormation stack and deploys itself. So to deploy a CDK.NET Lambda, basically you create an API Lambda. This is kind of same for all CDK. You set the runtime to .NET 6. This was written last year. And then you place in this code from asset, and you pass in the path to where your code is. One thing you need to do is the bundling of your application takes part inside a container when it's CDK. So you need to know a little bit about that container to put the right path in to tell it where to find your source. That's pretty much it. Once that's done, you've got a series of commands to build your application and then turn it into a Lambda package. You also need to configure permissions inside your CDK code. Permissions to publish to your topics, permissions to list your topics, and you need to configure your API gateway. I spent more time working on the CDK part of this than I did the MassTransit bit, even though the MassTransit bit is the bit I cared about. Once you're done, you can deploy your whole stack with CDK deploy, and then feed in CDK, and it will then deploy all your code. Up to a point, there's one slightly trickier thing to deal with here, and that's because the easy path for MassTransit is what we're looking at here. We put up a long-running server. So here's a server running .NET. It's got MassTransit inside .NET. It's a web service, and we configure MassTransit to use the queues. It will subscribe to those queues and receive messages, and it will send to those messages, and it will also create all the topics and subscriptions it needs on demand as it goes. Happy days. The problem with using Lambdas is we're not getting a long-running Lambda to open a connection to our queue and start receiving messages. A Lambda shuts down all the time. What we've got instead is our queues are being set up with a registration as provided by the provider. So the binding from the queue to our Lambda is a Amazon AWS thing we need to deploy. So we need to deploy some of these things first before we can bring our short-lived function up. So in order to do this, there's a console program And this console program has the switch, where is it? Deploy topology only equals true. I like to think this as the MassTransit equivalent of, or certainly the SQS equivalent of entity framework migrations. So I run this console program, give it the configuration, give it all the configuration of all my sagas and consumers I want, and this will run and it will create all the topics and queues it needs in the framework for me, and then I can deploy the rest of my application on top. And there we can see all the different topics and queues that get created inside Amazon. One thing I had a little bit of trouble with is getting the permissions just right. I found I could get all the queues deployed. I found I could get, it had a go at putting in the permissions, but in the end I just went in and edit the permissions and put in some stars. So every queue was able to receive messages from everything that had a certain prefix. So I had a prefix applied to all my queue names, and then used a queue name star to then set up permissions to allow everything to go around. So I had the right queues created, I had the right topics created, but the permissions between the queues and topics weren't quite right as deployed. And in the end, I just went and tweaked the permissions there. But a lot of that is just because AWS and Lambda isn't the kind of happy path for MassTransit. I'm slightly off the kind of the most beaten path. I think with Serverless Bus it's fine, and with RabbitMQ is kind of the most widely used engine. There's none of those kind of little bugs or things to work through. Obviously, when we are setting up our Lambda to subscribe to a queue, we need to know the name of the queue. So this is how we set that up in the CDK reference. So we ran that deploy topology only. It deployed our queues, and this is then how we configure that Lambda to say pick up this backend Lambda when there's something in the queue for us. And finally, in the Lambda receive message, we basically have a SQS handler. We've received an SQS event. What I needed to do here is receive the event and use a bit of JSON to go one hop in and get the message body. Basically that at this point, it's a SQS event JSON. Inside that is a MassTransit envelope, and I had to just get the envelope out and then feed that through to MassTransit, and it would then accept the message. And finally, yeah, here's all the JSON you get from MassTransit. So and in the middle there, you can see that's the actual core payload that we were sending. Okay, so we looked at a few things. Most importantly are those event-driven concepts. We looked at the use case, which is an online trivia game. And the thing I want you to take away really is those event-driven concepts and how MassTransit has these things that let you build apps using them. So you've got consumers, producers, sagas, and state machines. Then on top of that, you've got the ability to test your stuff, both unit tests, and the unit tests are really powerful. You can test your whole application without having to do any messaging at all. Then you've got persistence and integration testing to go further. And finally, at the end, I've managed to get it working deployed to AWS with CDK. All the code I've shown is online in a repo called MassTransit Trivia. And one final thing to note, I'm from Mantel Group and we are actively developing. So just Google Mantel Group, find us if you're interested to chat to our recruitment team. And I think that's everything I want to show you. So thank you. Questions?
You actually didn't mention the scheduling part. Because you mentioned the Saga persistence engine
Yeah.
and the queue mechanisms, but for the scheduling part, what did you use?
Yeah, I showed you. Hang on, I showed the scheduling.
No, I mean the scheduling provider. Is it like Quartz?
No. The way I'm doing scheduling, I missed scheduling as a way of sending messages. But if I go back through here, there is a way of sending schedules. But yeah, you can wire in schedulers like Quartz into MassTransit. But another way of wiring in schedules is to actually use a message transport that supports scheduling. So some messaging transports will let you post a message and say, here's your delivery date, and it will hold on to that message before it makes it available. So instead of having something complex like Quartz that's got to sit there on your server, or it goes somewhere else and Quartz sits there and puts it through, you can actually bake in scheduling just by sending a message with a delayed time in the future.
SQS supports this out of the box.
Yep.
It's called visibility timeout. It'll prevent
Yep.
the message from being visible to consumers. It's the same way that SQS and others in Rabbit as well implement backup. Is you give it a visibility timeout when it backs into the backup.
Yeah, with MassTransit it's a bit different. Maybe a bit different, but depending.
I will have a look at that because I'll double check that when I get to implementing. I've tested a lot in my test code. I haven't tested the whole system in the AWS SQS. So I might find with SQS not being the primary provider that actually scheduling doesn't work that well with SQS.
Yeah, because as far as I know, with Rabbit, which is like the base backend for
Yeah.
MassTransit, you do need to plug in an external scheduler,
Yeah.
whether it's Quartz or Hangfire.
I definitely know Azure Service Bus has very good support for scheduling. Yeah, so deliver out fields, yeah. Any other questions?
I think so. SQS cannot be like earlier means like the equivalent to the Azure Serverless. It cannot fan out. I believe it needs to be SNS and the subscription to the SNS.
Might be, yeah. Well, certainly the pub sub requires SNS and the subscription.
And then
I don't know. Yeah, I'll have to test the computing consumer panel a bit more with that one. Yeah. Okay. What about for FIFO queues? Because there's two types of queues. Yeah.
One is like sorted queues. That means
Yep.
first message comes
Yep.
first out in AWS one. The second is like eventual consistency. So
Yeah.
it's not guaranteed that we place first and second message. Consumer can have the second first and the first later. So like
Yep.
two types of AWS queues. So that's also considered.
Yeah, I'll look in that.
Sorted
I'll
queues are a little bit slower, and
Yeah.
you have to pay a little bit extra for it.
yeah. But I think,
there is another service called AppSync, which can be helpful, which
Yeah.
also is a fan out for the application integrations. If you are looking to the application integrations.
cool, I'll look into that. Yeah, I'll have to make sure that the locking and the computing consumer panel works well with
For the
that queue
schedulers,
provider.
there is a, Amazon Event Bridge, which has
Yep.
a scheduler. So
Cool.
It has like the similar to
Yeah.
what is this? Cron. It can run your Lambda every few seconds if you want. And the Lambda is its own like the warm up service, which is like the keep warm Lambda.
Yeah.
So it's costly. So like it can like cost can trigger in any way.
Yeah.
So you can keep warm your Lambda every minute. But the Lambda you can keep your Lambda warm max 6 minutes, 300 seconds. I
Yep.
believe. Then that Lambda instance gets destroyed and new one's created.
Yeah, and definitely with you talking lambdas and keeping lambdas warm, what I showed you was how you can run a web application, ASP.NET, pretty much with hardly any changes as a lambda. I'm not for the moment saying you should. It only works if your web API is very, very stateless, and all you're doing is just requests coming in, doing something small, and then shutting out. It doesn't matter how many different systems get brought up with that.
And you can take the SQS and the SNS
Yep.
on your local using the
Yep.
Amazon mock tools, which allows you like similar, like when you post your message in a MassTransit and how it wraps in the SQS and the body you are extracting. You can emulate the same effect using the Amazon Lambda mock tool locally, so you don't have to
Yep.
pay for that.
One of the key things, and this is across all serverless, you could be using Azure Serverless, Google Serverless, or AWS and Lambdas. When you want to scale up in response to load, you have to use a messaging provider that actually has those direct triggers from the messaging provider to your function apps. There's no point using Amazon queues with functions, because there isn't a trigger for functions. You'd have to wake up the function, get the function connected to the queue, and you've lost the point, because the queue needs to wake up the function.
Yeah, queue can pick up the function.
Yeah, but a SQS queue can wake up a Lambda, an Amazon, Azure Service Bus queue can't wake up a Lambda, but a Service Bus queue can wake up a function app. So it's that cloud, and they can stick to the same cloud for that key bit. That kind of, this queue can wake up this function. Another question? Yep.
How would you then like show that to the user? Because you don't want it to be like an asynchronous thing. It potentially
Yeah.
takes a while to then give them that feedback.
Yeah, that's a good question, and that's something I skated over because I'm focusing on the core function itself. But there could just be all users are sitting there with the screen open. There's probably some regular poll or regular receipt of what's the current state, what screen should I show. So, and that's not an operation that changes the state. It's just hit the saga, tell me about what's going on, and then get the response back without changing anything. But yeah, that's not something shown, but something I'm going to be building in once I start the user. Yeah.
Have some just
Yeah.
simple cache data object
Yeah.
in Redis or something.
That's it. You can just cache that, yeah, and have it updated whenever. Yeah.
Then, which would distribute this to the subscribers.
Yeah, but if you're waiting for it to act on the, when going through the queue and all that, that could take a little bit longer.
The idea is you don't wait though. You don't want the client waiting.
Yeah,
at any
exactly.
point,
So
right?
like, how would you best show the user that the action is being processed? Like, should you just like pretend that it was automatically
That's
processed
similar
on
to
the client,
any
or like,
other
how would you-
client that you would build where you'll find a user submits something and they're not waiting for it. It's just this has been submitted, and then they go back to whatever dashboard or anything, and you could have some notification pop up, or you could have any other kind of event to say that this has been done. You see the same thing with, say, AWS console. When you're kicking something off, you don't sit there and wait for it to actually deploy the service that you just asked it to do. Same with Azure as well, right? You kick that off, and then when it's done,
Yeah.
it pops up with a notification saying this is ready, right? It's the same with same UX that you would do
Yeah.
with any other client front end.
Transactions are a lie.
Yeah. But yeah, from say the user point of view, I've just submitted my answer, then immediately you can't submit your answer again. So immediately go, right, you've submitted your answer. I don't need to wait for anything else to happen. I know I've submitted the answer. Now, in the background, you're pushing into a queue. That's really quick. You don't then care how long it takes for that queue to get picked up. Obviously, you're playing games. You hope it's in a reasonable time, but it's not in that immediate request time. You submitted your answer. You're now locked from answering more, and now you're waiting for the state to change in order to move to the next question. And that's a much longer thing. And then the statement will kick off, and either you've got a polling process from the client saying, have we moved yet? Or you've got a signal R event coming back to your user interface to say, yep, we'll move forward. Yeah.
I'm working on something that kind of acts similarly to that. So I've got the
Cool.
this events, and then I've got a WebSocket that's sending those back. And so so if you act on it and you just like on the client side, you just pretend that it was automatically accepted. You just do
Yeah.
whatever you expect it to resolve.
I mean, one thing you can do is make sure your API doesn't say OK until it knows it's been queued. And once it's in the queue, then you're confident that it's been done, and it's just someone else's job to then finish up what happens next.
You just make messaging to the user a UX problem. Get a UX expert to deal with that, right? You don't need to worry about how you're going to handle that. You just say, it's going to be done. What message should I show to the user?
There must be a Brisbane UX user group.
Yeah, there has to be, yeah. Go ask any question at Brisbane UX user group.
But they won't use Blazor because it has
You
bad
can
UX.
put that on.
Yeah. Any other questions? Excellent.
Thank you very much.
Thank you very much, Brendan. Leave that on for a moment.